Good morning. For our project, we developed a novel and highly efficient microbial fuel cell as a way to produce clean energy and help clean up oil spill regions. Currently, our society faces a global need for a clean, accessible energy source. At the same time, we also need an effective method for remediation of environmental pollutants. Over 1.3 billion people lack access to energy. At the same time, the major fuel source, petroleum oil, is being consumed 4 times faster than it's being produced. At the same time, oil has high incidence of pollution, like the BP oil spill in 2010. Now, in an oil spill, a significant portion of the oil accumulates and sinks to the sediment floor, where it's very difficult to remove both artificially and naturally with microbial degradation.
Cleanup methods such as dredging is expensive, ineffective, and disturbs the environment. Without an effective solution, numerous organisms will be harmed.
Now, a microbial fuel cell can act as a solution to these issues, and a microbial fuel cell, or MFC, is a device that produces energy using the redox reactions in bacteria. And what happens is, in an MFC, bacteria form on the anode, and as they break down the organic matter, electrons are released and travel through an external circuit to produce a current, and they're then reduced in a cathode.
So how do MFCs relate to oil pollution? Like Kim said, there's a slow biodegradation rate due to the lack of available electron acceptors to facilitate the oxidation process of the hydrocarbons. Because MFCs have previously been used for wastewater treatment, we hypothesize that MFCs can be implemented in an oil spill region. However, despite these capabilities, current MFCs are not ready for commercial use because they produce relatively low power densities and use high-cost materials. So the anode requires further development because it is a site for bacterial attachment.
One of the most commonly used materials for MFC anodes is carbon because it's chemically stable and biocompatible. Recent studies show that reticulated vitreous carbon, or porous structures, have higher power densities because it has a higher surface area, which allows for more bacteria to adhere onto the anode. However, its power density is still low compared to its costs. The use of a natural organic material can act as a cheaper alternative in which a loofah sponge has a similar structure to RVC, and the carbonization of this material can create an electrically conductive carbon alternative.
In an MFC, an electroactive surface coating can enhance the anode properties. Graphene is a two-dimensional carbon allotrope that has high electrical conductivity and high specific surface area. Titanium dioxide is a popular semiconductor that it has low cost, high abundance, and high chemical stability. So a composite can be synthesized in order to utilize both properties from both sources and decrease the cost of graphene.
So the purpose of our project was to develop a more efficient and cost-effective MFC in which we focused on optimizing its power production and also analyzing its oil remediation capabilities. We specifically focused on engineering the anode by modifying its structure and surface coatings. We also looked at using the MFC towards applications of oil spill remediation to offer a passive, non-invasive method to current oil spill remediation processes. Based on the works of Logan, Yuan, and Zhao, we hypothesized that macroporous structures and nanostructured surface coatings will increase the overall MFC performance by improving the bacterial adhesion and extracellular electron transfer.
All research was conducted in our high school lab. We engineered 9 different anode designs, focusing on the variations of base structure and surface coating. A carbonized loofah sponge was used as a cheaper alternative to commercial RVC in Figure 11. Carbon fiber acted as a control. The capillary action test was conducted where the anode was submerged in a liquid in order to assess for relative surface area. Then scanning electron microscopy was used to visualize the anode morphologies. In phase 2, we evaluated hybrid surface coatings in order to use graphene's high electrical conductivity and titanium dioxide's high chemical stability. The composite was synthesized using a one-pot solvable thermal method based on works of Zhao.
So this is the process of how we synthesize the composite.
The cathode was prepared with a carbon base layer, 4 PTFE diffusion layers, and a platinum carbon catalyst layer. Then the anode was submerged in the sediment where the bacteria existed, connected with a titanium wire with the cathode floating on top.
So we implemented the MFC in 2 different systems, or organic sediment. We tested a natural marine sediment, which was collected from a benthos layer in a local saltwater area, to study how the MFC anode would react in a more natural simulation with mixed communities of bacteria. We also tested it in a simulated organic matter system to specifically study the oil degradation process, in which it contained oil-eating bacteria and oil. We measured the electrical output of voltage and current over a 10-day 10K resistor over a 10-day period for both systems. For the SOM system, we also analyzed the oil remediation process by extracting the hydrocarbons and then using UV vis spectroscopy to measure the absorbance. All our data for the power calculations, we calculated the power and power density using projected surface area to study how much power is produced per unit of material. For the oil remediation, we use a method based on Huenger and a calibration curve to determine the amount of hydrocarbons remaining after the 10-day period. All our data was analyzed for statistical significance as well.
The capillary action test showed that the loofah sponge retained the most water, indicating it has the highest relative surface area.
The SEM results that we took supported the capillary action test. And you can see here in figure A, the carbon fiber has very tightly woven fibers compared to the RVC and loofah sponge. In a study by Lepage, they found that under 200 micrometers, bacteria start to clog. And this could explain why carbon fiber is less efficient than RVC and the loofah sponge because it has an under 100 micrometer pore size. RVC is a glassy carbon material and has a much smoother morphology compared to the loofah sponge, which has this very wrinkled texture. The wrinkled texture can be contributed to the pyrolysis process, in which the shrinking of the plant tissues cause very wrinkled channels to form. And these wrinkled channels increase the surface area, which may allow for more bacterial adhesion for a more effective MFC performance.
For the electrical outputs for the natural marine sediment, we calculated the voltage, current, power, and power density. The x-axis represents time and days, and the different colors on the x-axis represents the different anode designs. The y-axis represents the corresponding electrical output. Statistical significance with a p-value less than 0.05 is shown by the stars according to the key. For the voltage output graph, the loofah sponge graphene and the loofah sponge composite has significantly higher voltage output when compared to the carbon fiber and the RVC. Because the cathode was kept as a constant, the cell voltage was an indicator for anodic potential. So the higher the anodic potential showed higher potential energy per unit charge. For the current graph, the loofah sponge composite has significantly higher current output when compared to the carbon fiber and the RVC. This shows that the composite has a higher charge transfer.
So for the power output, which was calculated using the following two measurements, as mentioned by Christine, the results correlated with the voltage and current. We found that the loofah sponge composite had the highest power output. Now for the power density, which was used with projected surface area, the results also correlated with the power output, in which between the structural groups, the loofah sponge was the most effective anode material compared to the RVC and loofah sponge. And this can be contributed to the SEM results, in which the loofah sponge had the highest surface area, which will allow for more space for bacteria to adhere on and for more electrons to be collected for higher power density. Interestingly, between the surface coatings, there was no statistical significance between the titanium dioxide and graphene, despite the fact that graphene has higher electrical conductivity. This can be explained by a work of Zhao, who said that titanium dioxide allows for hydrogen bonding between the microbe and anode, increasing the bacterial affinity. So in an MFC anode, the bacterial biocompatibility and electrical conductivity are just as important in power production performance. Overall, the loofah sponge composite had the highest performance rate, in which it was mean power density was 3 times greater compared to the control.
For the simulated organic matter system power density graph, the trends are similar to the natural marine sediment, indicating that the organic fuel source doesn't affect overall trends. In an MFC, the porous material allows for biofilm growth and a continuous flow of electrons. This is supplemented by the composite. Overall, in the loofah sponge composite, its open macroporous structure and its hybrid surface coating can synergistically enhance biocompatibility, electrical conductivity, and extracellular electron transfer efficiency. For the mean hydrocarbon remediation graph, all groups containing MFCs had a significantly higher percentage of oil remediated when compared to the no MFC group. This supports Liu's study that MFCs can be implemented in an oil spill region. According to Morris, the MFC anode in its solid state can function as an alternative electron acceptor and facilitate the oxidation of the hydrocarbons. Interestingly, only the loofah sponge composite has significant difference among the anode groups, with it degrading 93% of the oil. This indicates that for significantly enhanced degradation rates, optimal structure and surface coating is required.
We also conducted a cost-effective analysis to determine the economic viability of the MFC anode, and we had a power-to-cost ratio, and we found that the loofah sponge composite was over 26 times more cost-effective and efficient compared to the carbon fiber control. Now, some limitations to our project was since we were working in a high school lab, we were unable to conduct certain analysis, which we are currently continuing. We'd also like to test other hybrid coatings, like a polyaniline coating, to look at to determine the optimal coating. We also plan to test longer trials to see the stability of the anode material. So in conclusion, our results found a more effective and high-performing MFC anode, which was the loofah sponge composite, compared to standard materials. It also uses a loofah sponge, which is natural and sustainable, which may provide more accessible energy. Overall, our results show that the use of high surface area, electrical conductivity, and biocompatibility can synergistically affect overall MFC performance in both electrical outputs and remediation. Currently, we have a patent pending for our design and are continuing working on it. Some applications and the importance of our project is that it could provide clean, accessible energy in the future for remote sensors underwater, industries, and even developing countries. And also, it could provide a clean and passive method for oil spill cleanup compared to the current invasive methods.
We would like to thank the Manhasset Science Research Department for allowing us to conduct our independent study in a high school setting. And we would also like to thank Ms. Alison Huenger for the support throughout this journey, and the Siemens Foundation and Discovery Education for this opportunity. Thank you.
Thank you.